So welcome everybody. This is the San Francisco Big Analytics. My name's Chester Chen. I'm the organizer, one of the organizers for the meetup. So myself, I work at the GoPro and working on the similar field. So today we have two talks. So before we introduce the first speaker, I want to quickly go over some of the upcoming talks that we have scheduled. So today we have this two talks from one from LinkedIn, the other one's K Intelligence. So then, well, I don't want to skip anything. So, but we do have the list. Also have some other events by AI Camp, and one is organized by Bill is the ML Ops Global Summit, and then the other one is the AI Camp also organize another event called Auto ML Global Events. So you can, if you're interested, you can attend those. So our next event at the end of August, and also have two talks. One is about there's a project called Apache Submarine, and the other one is talking about one of the machine learning methods they call bootstrapping means for embedded language learnings. So the speaker, I just want to quickly mention that the second speaker on the speaker, and he wrote a, kind of a paper which is caused a lot of, sensation. Basically saying that reinforced learning is waste of time. So I have the blog on that. So, so I reached out to him. So, but he's going to talk a different topic. The other one is we have the early September. We also have another LinkedIn talk on the shuffle services. So please stay tuned. We have one more event I haven't really announced. Like likely October, November times. So we'll try to schedule two events together in that cases. So today, of course, we have a first talk from LinkedIn and Eric. Eric is the manager for LinkedIn infrastructures, the big data infrastructures. He has a lot of experience, and he gave just recently gave a talk on the data lake table formats, and comparing the three format. Delta Lake, Apache Hudi, and as well as Apache Iceberg. So, and if you're interested in that topic, you can go back to the YouTube channel looking for the video by the talk about Eric. And today's Eric's talk going to talk about the advantages of columnar formats, and we'll dive deep in this topic. So without further ado, Eric, please. I'm going to stop my video.
Hello?
Yep, we can hear you.
Can you see my screen?
Yes.
All right. Welcome, everyone. So today's talk is going to continue something about how to optimize your big data lake, right? I'm going to spend the next 25 minutes focusing more about some missing part about the columnar format. But everybody probably know Parquet ORC already, but there's some interesting stuff, you probably, didn't pay attention before. That's why I want to, bring the awareness to all of you. And so maybe when you go back to your company later this week, you can reevaluate whether you are making full utilization of the columnar format or not, right? If yes, great. If not, then, consider some new tricks. All right, so before I go into it, as usual, I will mention this topic was probably nothing really new. Since 2015, 2016 time, I have seen similar articles describing the internal feature about the columnar, about sorting, partition, vectorization, but this is 2020 already. When I talk to people around, I found just not many people really know about this kind of thing. That's why I decided to give a talk to mention this super important aspect of how to fully utilize the columnar feature to speed up your data lake and reduce your infrastructure cost. Okay. So let's just briefly look at the discrepancy between how the data ingestion happens and how the data are actually utilized or analyzed in your data lake, right? Today, most of the workload in your data lake are read intensive, right? The data are typically ingested once and read hundreds of thousands of times afterwards, right? That's why it is important to also optimize for the read access pattern. But I want to mention about the history, because most of the ingestion team want to keep it simple and consistent with the upstream. So in that case, you see a lot of reason, like if your upstream is Kafka, then you naturally will put everything as Avro. If your upstream has a lot of MongoDB, then you may see a lot of JSON dump, right? Of course, CSV and TSV are super popular here and there. It's very easy to, to exchange the format as CSV. But when you enter the big data era, all these kind of a simplicity actually may backfire on you, because you will not be able to get the performance, efficiency, and the cost savings that you are anticipated for your cloud data lake or your new generation of data warehouse, because queries are slow. Simple ETL job will run for a long time, and aggregate from the raw data into insight are kind of expensive. That's why in the second half of today's talk, you will see how Kylin is really addressing this problem by pre-aggregate and materialize all this business logic so that you don't have to query the super big raw data anymore. But in my talk, I want to see if there's something which is easy and simple that you can avoid the snowy list that data scientists are complaining about in your data lake. Okay, so before we go into the solution, I have a few thoughts here about why this happens, right? Because your application system actually prefer different things than your data lake. That is probably the root cause of all this, suboptimal patterns, right? To name a few, right? The online applications handles a single record at a time. So that simple reason will cause a lot of design pattern trade-offs and choice, for the data landscape you're dealing with. Okay, for example, because they are dealing with a single record, then super nested structure is actually a good thing, because you don't have to join, you don't have to repeat the redundant attribute anymore. You just cluster everything into a single nested blob, right? But again, at a later time, when you try to query billions of rows with nested structure, then you're going to struggle, and your computation engine will struggle, your CPU will struggle, your IO will struggle, your network will struggle. That's why we need to think differently, instead of what I call oversimplified end-to-end as-is pattern, right? That's why if we just carry all this listed pattern from our application system into your data lake, sooner or later you will find out something will go wrong or something will go slowly. Okay. So what really data lake want, right? Data lake is all about aggregation, batch processing, and the big chunk of the data crunching, right? That's why it is really aimed at a high throughput, and we're not looking at a single query. When I say query, means a single RPC call or single REST call performance. We're really looking at complex, ETL flow, ML flow, end-to-end, runtime, a couple hours, couple, 20 minutes, or even 2 to 3 days, right? So we try to optimize the end-to-end performance for a big batch job, right? And then if you heavily rely on the nested structure, that can really be a pain for your predicate push down. Okay, in the later time, we're going to talk a lot about how to leverage the predicate pushdown. The other one is, you guys probably use URN sometimes, right? URN is pretty popular in the REST microservice world. When you go to AWS and every resource is a URN, maybe you're doing URN for your own company's, internal entities as well, for your customer, for your inventory, for your product, for any service, it's a URN. But when you try to analyze this data, very often you just need the ID or the numeric portion inside of the URN. Then you have to run the extraction to get that part out, and so that you can do join, filter, and other operation against hundreds of millions of records, right? So when you're trying to do that, then you will see a significant slowdown because the suboptimal data type and the data format you're dealing with here. That's for URN. A couple of other things, right? CSV. CSV is super easy to generate, and it's also very fast to generate. But many people didn't realize to read and parse CSV is actually very, very inefficient. Even though it's a human readable, it's easily editable, but the parsing efficiency of CSV was horrible compared with Avro, ORC, and all these other binary formats, right? It is very CPU intensive. But of course, if you compare with JSON, CSV is still okay. JSON is even more CPU intensive when you really try to access a single attribute inside of the JSON blob. You have to write the JSON path to extract them out, okay? The last portion is typically with the modern computation engine like Presto, Spark, and Hive, and all this like Dremel, and even a GPU database, you often heard about something called vectorization or vectorized, okay? Vectorized thing is, parallelly processing the data cell together. Then typically they can be a couple of times or even 20 times faster than the row-based, non-vectorized processing. But sometimes, you don't have the right data format to take advantage of the powerful CPU and even GPU you have in place, because you have to first translate your data on disk from one format to another fashion, and then you pass that into your CPU and the GPU to process it. So these are all the areas that we should really think carefully. How can we take the full advantage of our infrastructure to make our data lake faster, easier, and nimbler for the consumers to use, right? Having said that, so these are the three typical usage patterns we often use for data analytics. One is filter, and I call it a big filter, because let's say if you have 5 billion records in your table, then if you need to discard 3/4 of them, then this is something we call a big filter, because even though the remaining quarter of the data is only 1/4, but it's still a huge one, right? But consider how many records you will eventually discard by your filter. So the cost to kind of eliminate those 3/4 out of 5 billion records could be significant, because in that analogy, you could spend 40 minutes process your data, but maybe 20 minutes out of this 40 minutes was doing nothing but try to go through all these 5 billion rows and discard 3/4 of them. So that sounds like a huge waste of your CPU, network, and all the computation resource, right? So that's why the big filter is a very important pattern in data lake we should optimize. So the typical way we can do is to add partitions or sub-partition to that, so that we can skip a lot of unnecessary data without even scanning those records, right? But sometimes, that is hard is hard to achieve, then we can go to the second choice, which will require the sorting of the records based on the filter fields. And I'm going to spend a lot of time talking about that one today, because that one is pretty much unknown by the community as of now, okay? So the second usage pattern for analytics is called a join, but it's called a massive join, right? It's a big table, join big table. One table is like 20 million rows. Another table is 500 million rows, right? This kind of a join is very expensive. Sometimes you also do a lot of metrics computation, which is group by on top of such big table. They all need something, the pattern that we call hash distribution, and then sort, and then aggregate, something like that. So that's why there's a typical optimization we need to consider is bucketing the data set accordingly so that we can reduce the shuffle, right? Chester just mentioned, in October, LinkedIn is going to talk about Magnet, which is an attempt to optimize the Spark shuffling. But at the same time, the bucketing is really a good complement to say, if I can make the operation shuffle less, right? Then, the computation will be much more cost effective, right? So in addition to make your shuffle efficient, you should also explore the possibility that you can eliminate the shuffle once for all, right? So bucketing is definitely one of the solutions. You should take a deeper look at it. Okay, the last one is lookup, right? Lookup is frequently used in any ad hoc data exploration. Let's say, for example, you want to take a look at particular user's behavior, or you want to look at a particular product's performance, right? So you're going to filter out the massive amount of a data lake data, but just try to find that particular user out of the haystack, right? So this one can also be optimized either by sorting the data by the lookup ID, or you can also use bucketing again, okay? So now let's look at the typical way how people are doing that, right? So first of all, partition pruning is a well-known strategy and the tactics that we all use. What I'm trying to talk here is, let's be intelligent to use a multi-level partition, because some companies, they only use one level of partition, right? It's probably just a date, but actually you can use 2 to 3 or even 4 level of a partition to cater to your query patterns, that a lot of the predicates push down can happen at the metadata level. When I say metadata level is when the High Presto and the Spark, when they plan the query, they can use the metadata to skip all the partitions without even scanning a single byte from the data file at all. That is the most efficient query optimization you should leverage, right? So in this particular screen, I give you one example is, within each hour partition, you can potentially split the records by active records and the inactive one. The rule of thumb is, if the inactive portion is too small, okay, I can say if it's smaller than 10% or 15%, then I would not recommend go with partition, right? Because these two partition, active partition and the inactive partition, the size could be highly skewed. In that case, when you try to produce and maintain such partition, your ETL job or your ingestion job will suffer from that skewness, and eventually the active part will take longer time, but the inactive part will finish very quickly, but your overall ingestion time will be pretty long. And at the end, when you try to leverage the partition pruning, since your active records is about 90%, and if most of your query is hitting the active records as well, then you don't really eliminate a lot of the inactive records. That's why when you try to go deeper in the multi-level partitioning, you should also understand your data distribution. So one thing I want to call out here is please avoid the tiny partitions, right? If you have too many tiny partitions, it will actually hurt your performance and put more pressure on your storage layer. So if your filtering field actually have more than, let's say, 60 values in it, and some of them were highly skewed, means some are more popular, some are very less used. So you should consider the sorting instead of partitioning here. Okay. So now let's talk about the real thing I want to really talk about and emphasize today is about how do we get the better compression ratio of Columnar and also leverage the skipping index to speed up your query performance, right? Because many people think, once we convert our data type from row-based into columnar-based, problem solved. We're in a very good shape. But actually, there's a lot more you can do beyond that. So the picture just show you that if we sort the data properly, we can put the similar value and identical value next to each other. And when this is processed by the columnar compression algorithm, they can be compressed much more efficient than just a simple dump of a columnar format without the further sorting. Okay, this is applicable for both Parquet, ORC, Avro, and any commercial columnar implementation. Okay, so this is the main thing I want to talk about today. So following this, I will show you a few things, how this is working and why you need to pay attention to it. So number one reason is, the query patterns. If you also agree that you do a lot of a big filter, then you understand how efficient the filter can do for your query performance. That's why we try to optimize the skipping index in the columnar format so that the query planner can take advantage of this skipping index, right? The skipping index is nothing about the min max, and sometimes they also provide a Bloom filter about the value within that data blocks. So that, if your data is sorted, those min and max can definitely tell the query planner how to skip the data blocks or how to access the data blocks if the required ID or attribute value exist in that data blocks, right? So this is mainly about doing the same for less, because you don't want to waste your time scanning those data files, data blocks, which will end up being discarded anyway. That's why we need to tell the query planner through the skipping index how they can work smarter, right? So the second reason is, as you see the picture before, if we actually put the repetitive value next to each other, you can easily imagine the compression will be much more efficient, right? So that's why we try to leverage the sorting to help you gain two goals. So let's look at one clickstream example, because everybody probably understands the clickstream because it's typically used in a lot of these examples, right? So let's assume in your clickstream data, 40% of them were guest traffic, means people didn't log in, and 60% people actually logged in with their user ID. And also, you constantly or frequently filter all your traffic by the page ID, right? Because the page ID will show you this is a home page, login page, message page, or products page, or purchase page, or that kind of thing. It's a very, very meaningful filter. So for this kind of a gigantic data, let's assume we have 10 billion events per day, right? So what is the recommended layout here is, first you need to partition the data by date, hour, and the guest traffic, so that you can split within each hour, 40% goes one partition and 60% goes another partition, because we anticipate a lot of your query no matter it's ad hoc or scheduled ETL or machine learning feature generation, will only target either the guest or the logged user. So by doing this isGuest partition, then you can easily avoid scanning the other 40% or the other 60% of data files, right? So that's number one. The second one is we will do a distribution. The distribution here is really trying to improve the sort performance to avoid the global sorting bottleneck. That's why we choose something has a high cardinality, right? Has a lot of distinct value, such as cookie ID or IP address together, so that you can evenly distribute your data into all these sorting buckets for you, right? The last one is the real kicker, right? When you sort the data by page ID and then by the user ID, then you can imagine when your query actually have a filter column for page ID or user ID or page ID plus user ID together, then the skipping index will work really efficiently with your query engine to figure out how to only scan the data file and the data blocks inside of the data file for the qualified records. And that's the three level of a file layout optimization. One thing I want to call out here is, we probably should not do global sorting for any big data set. But if the data set is less than 50 gigabytes after compression, you can still consider doing a global sorting, because a global sorting is a highly optimized layout. If you do any ID-based lookup or join, the query will be highly optimized, right? Okay. Here is the final example, right? So let's say that 10 billion rows daily partition in Avro is about 2.7 terabytes. If we just simply dump it to ORC, it's 1.9, which is 30% smaller. This sounds pretty good, right? But if you haven't attended today's talk, and you probably end up there. But okay, when you go back, you can do another round of optimization. Then you can reduce that 1.9 terabytes down to 1.3 terabytes. That's another 30% down, okay, of the size. Don't you love it? So you should try it, right? But what really comes next is even more significant, because your query performance suddenly after the sorting will just go through the roof. Because if you actually apply the isGuest equals either 0 or 1 kind of filter into your into your query, then your query will suddenly run much faster, right? 60% of the IO, you actually apply more selective filters such as page ID or even user ID into your filter. Right, you can imagine a lot of your ad hoc query or this kind of like a deep dive query will have very precise filter criteria. Then you will suddenly see this kind of query will only cost you 10% of the IO than ever before. And the query finished within no time. Okay. You used to have to wait for 20 minutes before the Hive to finish, right? Now, even Hive finish within a minute. If you use Presto, it's literally 5 to 10 seconds. You get your answer. And you have never had such experience before. That's why if you're a data scientist, machine learning engineer, or data engineer, you will be super happy about your experience of dealing with this data. Sounds pretty good, right? But we have to make some trade-offs, right? The first thing is typically people may wonder, why should I optimize for query performance instead of compression ratio? Okay. My answer here is I care more about human productivity. The human here means all the data users, right? And I also think query performance is more important than storage footprint. That's why I always choose to optimize for human instead of storage. Okay, just my personal choice. The second one is, and the subpartition sounds pretty complicated because you cannot really do it with skew data, and you need to make sure the partition fields cardinality was pretty low, and this sounds like too many restrictions to me. So why don't we just simply sort everything, right? We don't have to do subpartition. So the answer here is actually because partition pruning have level, and those metadata are relatively simple, right? You have like 100 partitions or something. So you only have 100 entries to process to decide how do you do partition pruning. So that's why partition pruning is still about 100 times cheaper and faster than skipping index, okay? Of course, the iceberg and the delta lake will try to make this maybe 10 times cheaper only instead of 100 times cheaper, because they will kind of like consolidate all the metadata together so that you can make this partition pruning a little bit faster. But still, the true partition pruning based on metadata is always better than using the skipping index. Okay, keeping that in mind. The second one is sorting is always expensive, right? Because if you think about partitioning, it's a map side operation, but sorting is a reducer side operation. So that's why reducer side operation is typically a couple times more expensive than the map side one. So you need to pay that cost. So that's why if we can do something at the partition level, we should do it first. And only if we cannot do it properly or efficiently, we will go to the sorting. Okay, so the last one is, some people think, oh, this sounds great. Your example looks amazing. I got like 5,000 tables I want to optimize. Can you just give me some simple formula that can apply to all of them? I say, no, sorry. This has to be done case by case. Then suddenly people turn their heads away to say, okay, I'm not going to do this. This is too like customized, right? My suggestion for this is you don't have to optimize all your table because not every table is worth the effort. You should only apply this optimization to a few mostly used but also big table, right? If the table is not big, why bother? If the table is not frequently used, why bother, right? So please don't be overwhelmed by this trick. Say, okay, I have to either adopt it for every table or I have to give it up for all my tables, right? You should really start small. The second one is, please don't treat this as an infrastructure only initiative, right? You need the feedbacks from your user communities, because the data scientists and the machine learning engineers, they really know how they want to use the data and how often they use it, how do they use it, and where is their query pain point, right? So listen to them, gather their feedbacks. That can help you to deliver a better data set to them. But second, you should always tap into your query log analytics, right? That is the most effective way to figure out how you can optimize your data file layout for your precious data lake. Okay, if you don't have that query log analytics built yet, please consider build this. Okay, a few caveats. I'm gonna skip this very quickly. You can always go back to look at the slides at a later time. Just try to make sure when you try to use bucketing. Right now, the bucketing in the open source world is still not in a very good shape, because Hive and Spark are still not talking to the same language in terms of bucketing, so that you have to be careful about that. But sorting wise, I think we're in pretty good shape, and you can take full advantage of it. Last but not least is about, if you can store your data in a numeric fashion, such as integer and big int, don't use URN or other string format, right? That conversion, it is definitely worth it, especially when you use a columnar data format. The join, scanning, compression ratio for the numeric type is way, way, way better than your string. So, sacrifice a little bit about your human readability or the schema consistency, and you will gain a lot of performance back in your backyard. All right. So, summary. Why most of you haven't heard about this yet, right? You came to this meetup, you feel surprised why we're talking about this one. Yes, as I mentioned earlier, this topic was not really well known by the public so far. But in reality, all the commercial cloud data lake vendors through Redshift, Snowflake, BigQuery, Vertica, and all others, they have had this sorting and the subpartition for many, many years already, right? Their business model and their business value heavily rely on all these features to provide the great performance to their user, and that's why their customer are paying them for. Okay, but unfortunately, in the open source world, all these were still in a relatively unknown state. Even though the feature was there, but the public awareness was very, very low. And of course, their cost-based optimizer will still have a long way to catch up to fully take advantage of all this layout optimization. That's why I feel compelled to give this talk today, so that you, as an audience, will understand why these features are important and how you can make full utilization of them. All right, so to wrap up my slides, and this talk slides is available in this link already, and I do have another detailed blog to explain all the caveats. I'll give you a couple of different examples of how to build this sorting subpartition structure for different kinds of data sets, no matter it's IoT, operational metadata, or just orders, e-commerce data. So feel free to take a look and see if any of them resonate with you, and you can become a believer to make a full utilization of your columnar data format in your data lake. Thank you, everyone. Chester, back to you.
Yeah. Okay, that's a great talk, and I can see that. I probably can use the trick that looking my own data lake. I know the timing is almost perfect, and we still want to take a few questions, and then we'll give a second speaker extra time. Since we could push out a few minutes. So anybody has questions, please type to the QA section if you can. So let me try to see any questions here. So far, I haven't seen any questions, but if you do have questions, type the questions for Eric. So I give a couple seconds. If not, and you can wait for later. When all the speakers finish, you can still ask questions after that. Okay, seems no more questions. Again, thank you, Eric. This is actually total excellent talk, and I wish I know a lot of these details and apply it in my own work. Our second talk is from Kylin by Kai. He's going to introduce us to the Apache Kylin. So Kai, please take away.
Thank you, Chester. Yep. Hi, guys. This is Kai. Let me share my screen. Okay, are you able to see my screen?
Yes.
Okay. And thank you, Chester. Thank you, Eric. That is very great presentation. Actually, I'm inspired by a lot of the details you present. I think we can leverage those details in Apache Kylin as well, because actually Apache Kylin is trying to implement a new columnar storage-based engine, which is based on Parquet. And I think all those topics you shared today can be used in our new storage engine as well. Thank you, Alma. Thank you so much. So I'm going to start today's topic. So good afternoon, everyone. And today I'm going to discuss how to guarantee exact consistent queries with sub-second level latency on massive dataset. So this is today's agenda. First, we will take a look at the scenarios where contesting can help. And then we will do a demo to look at the contesting query performance of mainstream query engines. Next, we discuss how to achieve sub-second query performance in Apache Kylin and what is the technology behind the scenes. And finally, we will take a look at the real use cases provided by community users. Okay, so let's take a look at what is contesting. So contesting is a way to compute the number of unique values in this set. For example, here we have a table that records all the click events of the user access in our website. Assume we want to know two very important metrics, PV and UV. I'm pretty sure you already well know about these two metrics. So they are page view and unique visitors. They indicate how many access traffic we have totally and how many different users our website has. So for PV, it's quite simple. You can just count how many records we have totally. But for UV, we usually need a contesting function. So in this example, we need to find the user name column and remove the duplicate values and count the number of different values. And then we get the UV is 3. Quite simple, right? But imagine that if there are tens or billions of hundreds or hundreds of billions of records that need to be counted, it will become very complicated and time consuming. Okay, so actually there are two types of contesting. One is approximate contesting and another one is exact contesting. For approximate contesting, it uses a statistical estimation method to calculate the results. It's not accurate and allow errors. Approximate contesting is faster and use less memory and CPU. It is usually used in some chain analysis scenarios. In these scenarios, accuracy is not necessary. You only need to know the general chain and can accept the existence of errors. But in most of other scenarios, approximate contesting is not good enough. For example, if we turn the error into money, it will become more intuitive. Assuming the correct result is $1 billion, if we are using approximate contesting with 1.22% error rate, it may produce an error of $12 million. That's a lot of money. So it is often mandatory to use exact contesting in some scenarios, especially related to transactions and money. So usually users, they need to know the exact and accurate number of distinct values in below scenarios. Exact contesting can guarantee the accuracy of result, but it is slower than approximate contesting and require more computing resources. Suppose you advertise your product and pay according to the numbers of ad clicks. Then you definitely don't want the billing to be measured by approximate contesting. Okay, so let's go ahead to look at some common exact contesting scenarios. The first one is data analysis for website or mobile applications. Then when analyzing the usage of website or mobile applications, we often need to understand some very important metrics or answer some questions. For example, what type of people are our users? Where do they come from? Or what kind of people are most interested in our product? This usually can help us better target customers. So there are two very important and frequently used metrics here. The first one is unique visitors, UV. We mentioned that before. And another one is the daily active users, DAU, or monthly active users, MAU. Decision makers, marketing or product people, they all need to know these metrics to help them make strategy to improve products and make profit. to get those metrics, you have to use exact contesting. Another common scenario is user behavior analysis. Retention analysis is frequently used, which analyze the numbers of customers who visit continuously in different time periods. For example, 10,000 customers used our products on Monday, and how many of them continue to use our product on Tuesday, and how many is left on Wednesday. Retention analysis helps us understand customer loyalty, identify the audience, and also helps analyze product that can be improved. In order to calculate the retained users, we need to perform deduplication calculations on the daily users. Extract exact contesting is required in this scenario. If the number of users and visit is huge, then retention analysis will have high requirement on the performance of the query engine. I guess it won't be a pleasant experience if you pick a date range in this chart and have to wait for 10 minutes or even half an hour to get a result. So we need an interactive analysis here. So the performance is very important. Another scenario is the funnel analysis. For those behaviors, including a series of steps, users may be lost in any step of them. For example, a purchase behavior. Users, they need to do a couple of operations to complete this purchase process. And we need to analyze these steps to find out which step has lost most users and can be improved. Or analyze what type of customers are more likely to be lost in a certain step. Let's go back to this purchase example. If we observe the flow of purchase behavior, the customer will first enter our shop and then view the details of product, check out, and complete the purchase. Assuming that through the funnel analysis, we observe that more customers are lost during the checkout step, then it is likely that our checkout experience is very bad. Do customers have to wait in a long line? Is their system stable enough? With such analysis, we can improve the user experience, thereby retaining more customers and facilitating more orders. To achieve this, in each step, we need to perform contesting. And we need to know exact number of users lost in each step with exact contesting. Okay, so we discussed what the scenarios need to use contesting and why it is very important for this analysts. And also know that there are two kinds of contesting, of which exact contesting is very important for many scenarios. But normally on a very large scale dataset, performing exact contesting is always a big challenge. So next, let's analyze from the perspective of technical principles why exact contesting is so difficult and how Apache Kylin solves this problem. So earlier we mentioned that approximate contesting is simpler than exact contesting. Actually, there's a mature and a proven solution for approximate contesting already in big data industry, which is Haplot law. We are not going to discuss too much about this algorithm. Let's focus on the exact contesting today. So for exact contesting, when processing massive data, it will face following challenges. The first one is data volume. It needs to scan all data, which will lead to poor query performance. And secondly, because the contesting matter is non-cumulative, it is impossible to derive the relevant value from the calculated value. For example, if we already have the result, the UVs for the 7 days a week, and we want to calculate the UVs for a whole week, we cannot simply accumulate the 7 days data to get the final result. So we still have to go back to the source data and scan all the data and recalculate it. Similarly, in addition to not being able to do a roll-up operations, we cannot directly perform their logical calculations. And even only one exact listing needs a large amount of calculations. How about the whole dashboard? It will generate several or even more exact listing queries at the same time. So good luck to you if you have to refresh this report. All right, so we talked about the exact listing challenges in large amount of data. You may still not believe it. So let's take a look at the performance of the current mainstream query engines. Let's see how they perform contesting queries on large amount of data. We choose Snowflake, Google BigQuery, AWS, and Apache Kylin as a comparison. Okay, here I have a video recorded before. Let's check this video. Now here we have the Snowflake opened, and let's try to run some queries against the TPCH 1000 benchmark, which is a very popular benchmark dataset in big data area. So first of all, let's clean the cache, and then let's try to run the count distinct query on the order key. All right. So in this dataset, we have 1.5 billion rows, which is a distinct values. All right, let's keep it running and switch to Google BigQuery. The same dataset, TPCH 1000, and the same table orders. Let's run the same query, count distinct order key, against this table in Google BigQuery. All right, it's running. You can see their times it's spent are shown here. All right, let's switch to the AWS. I need to move this, go down. All right. Again, same data, same table, same key, and run the count distinct. The last one we are going to take a look is the Apache Kylin and TPCH 1000 orders order key. That's right. All right, it spent 2.9, almost 3 seconds to get the result. And you can see the total record is 1.5 billion. And let's switch back to the other engines. Asina. Yeah, Asina is also finished, but it spent 24 seconds. And it scanned 50 gigabyte data to get a result. All right, how about the Google BigQuery? Yeah, it's finished as well. Oh no, this is the last result. It's still running. So for last run executing, I spent 1 minute and 40 seconds to run this query in Google BigQuery. How about Snowflake? It's still running almost 2 minutes. All right, I'm not going to wait for Snowflake. And I actually already prepare a testing result here. I'm doing a lot of runs of testing, and I put the average latency here. So in this graph, we can see Snowflake spend almost 200 seconds to get the result. And AWS is better. The average time is 50 seconds. And Google BigQuery, it spent almost 100 seconds to get a result. Apache Kylin spent almost 2 seconds or 3 seconds every time to get the result for the 1.5 billion rows. All right, that's a result. Okay, so that is a demo, and I put the result here in the slides as well. You can check it out later. So a little introduction about our company. Kylin is a company behind the Apache Kylin, and Kylin is a Kylin plus intelligence, and it is a commercial version of Apache Kylin. Let me just give you a quick introduction about this company. And Intelligence is focused on actually it is founded by the creators of Apache Kylin in 2016. And it provides the enterprise features on top of Apache Kylin by leveraging the AI technology, and Intelligence can make the OLAP models and the cube smarter and gain better performance and reduce the significant maintenance efforts. Intelligence is keeping leading and contributing to the open source community, just like the other open source projects. There are always commercial companies behind the open source project to help make the community better. For example, Spark and Databricks, Hadoop and Columnar, Kafka and Confluent, etc. Okay, that's a brief introduction about the intelligence. Okay, so we demonstrated Apache Kylin's query performance on large data volume. So how does it work? What is the principle behind the scenes? Let's take a closer look at from the perspective of technical. Okay, so actually the key points are quite simple. There are only 3 key points here: pre-aggregation, bitmap, and the dictionary. Okay, let's take a look at them one by one. The first one is the pre-aggregation. Pre-aggregation is actually is the core principle of the whole Apache Kylin, not only the context thing. By calculating the result to be obtained in advance and storing them in the queue, it will avoid lots of the on-the-fly calculations, so that it can save significant time and computing resources on each query, and then thereby obtaining faster query responses. So let's take a look at this example. In this table, we record the website page that users visited on different days. Actually, we have this example before. So suppose we need to calculate 2 measures, the PV and UV. Through the pre-aggregation, we can store the result in another table. We call it a result table or intermediate table. For example, we store the PV and UV for April 1st in a new record in this new table. And add another record to store the result of April 2nd. And then the query comes. We do not need to scan the original table. And we can just fetch the result from the result table directly and return to the users. Okay. In addition, suppose we not only want to understand the daily situation, but also need to know the summary of maybe the past 2 days. So what should we do? Can we just summarize the record in the result table directly and get a final result? So for PV, we can do that. We can just fetch the 2 records and add them together and get the final result. But for UV, because we need to do the condensing, we cannot simply add the 2 values together and get the final condensing result. It seems that pre-aggregation does not work with condensing. Let's think about this again. So the reason why condensing cannot be accumulated is that condensing result in this result table is just a value. It does not contain any information that can be used to do a further aggregation. What if we store some information in this intermediate table instead of just store a simple value? Can we do the pre-aggregation again? Yeah, the answer is yes. So in order to make this happen, Apache Kylin introduced a bitmap. So what is a bitmap? Bitmap is a special data structure. It uses a bit to indicate whether a value exists in a dataset or not. Everyone knows that the smallest unit of information stored in a computer is bit. And the use of bitmap can effectively save the storage if the capacity of the original data is very large. Storing the original value directly consumes a huge memory and storage. Then it's a good option to store it by converting to bits with the bitmap. For example, as shown in this figure, the original UID is an integer type, and which occupies 4 bytes, that is 32 bits. We can reduce the storage space by 32 times by converting it into a bitmap. So how can we do that? Actually, quite simple. Each UID can be mapped to a bit based on their value. Let's take a look at the first row in this table. So the value of the UID in the first row is 1, and then we can put the value in this bitmap. The order of the bit 1 is 1. That means it has the value 1 in the original table. And similarly, we can put the value of 2 to the second order of the bitmap. And by converting all the record to the bitmap, we can have a bitmap contains all the data of the original table. So that's how we convert the original table to the bitmap. With this bitmap, it can not only save the storage, but also the operations of bitmap can effectively use computer native instruction and have faster operations. In addition, bitmaps can often have other compression method, which can make the storage even smaller, such as using different storage structures according to the sparseness of their data, or storing consecutive numbers briefly. Actually, that is the same idea as Eric presented before. There are many bitmap implementations in the industry. And in Apache Kylin, we use a roaring bitmap, which is a bitmap implementation with very good performance and has been used by many mature products. Okay, so let's see how Apache Kylin leverage bitmap to implement distinct pre-aggregation. As we mentioned before, instead of storing their simple value, integer value in the result table, we can use the bitmap stored in the intermediate table. And then we can use the bitmap we stored to do another round of aggregation. So with that, we can have the distinct pre-aggregatable. Okay, that is the secret how Apache Kylin can achieve the purpose of a rollup on distinct. Okay, so the bitmap not only provide the benefit of the storage, it can also, as we mentioned, it can also accelerate the some operations. Actually, there are 2 common operations on top of bitmap. There are AND and OR. So AND usually used in the scenarios like retention analysis and funnel analysis. And OR is usually used in the cross dimension analysis, which is a common scenario in the multi-dimensional modeling. All right, so we talk about the pre-aggregation, we talk about the bitmap. But we all know that bitmap can only store integer type values and cannot handle string type values. But in the business, we often need to use string type values such as usernames, emails, etc. So how does Apache Kylin handle those type of data? To solve this, Apache Kylin introduced the concept of dictionary. Dictionary is a common encoding method which converts character strings into numbers by one-to-one mapping, so that you can use a bitmap to store the converted numbers. In this example, we use a dictionary to map the username into integers. Like this, we extract the username and we assign a unique value for each username, and then we have the encoded integer for their string type. And then the problem turned to the original one. And then we can use this encoded value and store it in the bitmap to do the pre-aggregation. Okay, that's how we use a dictionary and a bitmap together to handle the string type data. Okay, that's all the three key points Apache Kylin used to accelerate the queries with contexting. Next, let's take a look at use cases shared by the users in the communities. So the first use case is from Manbang, which is the largest Chinese truck logistic startup company. There are more than 7 million registered trucks and 2.25 million active users. They have currently launched 8 mobile applications and generated more than 10 terabytes of data in the last 2 years. They hope to use Apache Kylin to do retention analysis and funnel analysis on a wide range of dimensions and the data range. In addition, they also hope to use Apache Kylin for user profile analysis. This is the technical architecture diagram shared by Manbang. Let's take a look at from left to right. Manbang collects data from mobile applications, website, and the log files. The data is sent to Kafka, and then the data is divided into 2 process methods according to the different types. One is sent to Hive. After some ETL jobs, it is loaded into Kylin by day. And another kind of data with real-time requirement is directly connected to Kylin. Apache Kylin is responsible for modeling data and the pre-calculation work and exposing the query services to the front end through the RESTful API. Here's an example of the retention analysis in Manbang. Because Manbang is a Chinese company, so we only have this Chinese version screenshot. I hope it won't affect your understanding about this case. Manbang independently developed this front-end analysis system to provide self-serving analysis for their end users. So analysts, they can choose any type of behaviors they want to analyze. And they can choose any time range in this chart. After submitting the filters, retention rates are calculated at milliseconds level and returns to the users quickly. This greatly improves the analyst's work efficiency. At the same time, it is hoped that the analysts, they can perform a flexible funnel analysis. So by saying flexible funnel analysis compared to the traditional fixed template funnel analysis, the difference is the users can combine different steps to customize the funnel as they want, so that the business can be flexibly analyzed to find the weakness or anything that can be improved in the product. And users can choose any 2 steps in the funnel. And after choose the 2 steps, all the user details will be shown in the bottom of this dashboard. And they can use the details information for further promoting events. Okay, and another case is from Didi, which is the #1 rideshare company in China. The latest figures show that in December 2019, their monthly active users reaches 19.2 million. And the average daily order of the year was 24 million. Didi mainly use Apache Kylin to perform user profile analysis and precision marketing. Using Apache Kylin to build a user profile, you can conduct precision marketing based on user portraits. For example, by analyzing different user categories, find a specific type of users, and send coupons to them to promote their consumption. Similarly, in order to increase customer loyalty, Didi will also select different specific types of users based on their user tags and upgrade their cars for free, for example. Through this kind of activities, DD increases customer stickiness. In addition, for some promotional activities, the result need to be analyzed to evaluate the effectiveness of the activities. Through the statistic of new customers or returned customers, we can determine whether these activities have achieved the expected result, or we can decide whether to continue to organize the similar activities or improve the activities. In the process of determining the target user groups or to calculate the user tags, a large number of exact constants are included in the whole process. In a traditional way, it usually took several days or even weeks to group users and calculate the tags. Apache Kylin helped DD reduce the whole workflow and help the analyst get the result very quickly. Okay, at last, let's take a look at the use of Apache Kylin in DD. At present, the amount of data processed by Apache Kylin exceeds 200 terabytes. They are distributed on more than 5,000 cubes, and more than 7,000 tasks are running every day. And a total of 7 clusters are set up, Hadoop clusters are set up to cover multiple business lines of DD. Okay, that is all I want to share today. And if you find it helpful, and if you are interested in Apache Kylin, please don't forget to join us. You can participate in the community by forking our project in GitHub and help us to review the code or contribute some patches. You can also subscribe our mail groups, and you can also join our Slack channel. Okay, thank you very much for joining today's meetup. Thank you, and I will get back to Chester.
Thank you, Kai. Actually, it's a very interesting talk, and actually myself have 2 or 3 questions that I want to ask. But before that, we got one question from the community. This question is that for Bitmap, what is the UID distributions? It's very sparse, like for example, 1, 2, 3. And then like the next one is like 9 million or 900,000 or something. 9
Yeah.
million. So,
yeah. Actually, this is a very common scenarios and a very good question. So actually, Apache Kylin does not do too much about their compression of their data because we are leveraging the Roaring Bitmap, and the Roaring Bitmap has compression against the data. For the sparseness of the data, it can handle it well.
Wanting, if you want to continue follow up this question, you can type to the QA side. Okay, I got a couple of questions for your talk. And the first one, so who's what's the other softwares in the similar space and in the Apache Kylin? And it looks, you know, I think before the meetup, I asked you about compare with Apache Druid. One is real-time OLAP, and in your cases, you said it's a more batch-oriented OLAP. But it's from the use cases, you also see that it's sub-milliseconds of responses. So it sounds like they're in a similar space. And what the others space? That would be first question.
Yeah. So as you said, Druid is a streaming OLAP. So Druid is great. It always adopted by their users if they have their real-time scenarios. So Apache Kylin are more focused on their batch data, historical data. It's like a batch manner to process the data. Apache Kylin also has the ability to process the streaming data because we have Kafka as our data source. Before the latest release, I mean Apache Kylin 3.0, before this version, we have some gaps. I mean the gaps between the data generated and the data can be consumed. there will be like a minutes level gap. So even we are using Kafka to feed the data to Apache Kylin, we cannot consume it immediately. We have to wait for like a few minutes to build a queue, and then we can consume the data. That's why we say Druid is maybe a better option for the real-time streaming. And after the new version, Kylin 3.0, we introduced a real-time architecture, which is contributed by eBay. That feature is officially released, and we have some feedback from the community, but I'm not sure if there's some real use cases can be shared in the community. As I know right now, maybe some users, they are trying to use these new features, but I don't have too much information from that. So simply, if you have real-time scenarios, I would suggest use Druid. If you have a batch manner data processing, Apache Kylin will be a better solution. And other than Druid, there are also some other project or product in the market, like ClickHouse, like a Presto. Maybe they focus on different area, but typically they can use as an OLAP layer as well. But normally they have some difference between those products. And there are a lot of comparison report in the community. You can search for the comparison report as well.
Okay, so my next question is related to the use cases. So the last use cases you're referring is in the real realm of marketing. So basically using Kylin to build the marketing, So there is a growing trend of industry doing the so-called customer data platform, which is Target is doing exactly that. So so in your two use cases, you're talking about whether it's a precision marketing, so user segmentations, or channel marketing, all that stuff. So those are usually built by specific vendors in this customer data platform space. Are you saying that the use cases that you're presenting by DD, they're basically building them themselves and they're using Kylin as a backend?
Yeah, so actually Kylin is not designed specific for this kind of scenarios, right? Kylin is a generic OLAP layer. Yeah, the users, they need to customize some development work based on their scenarios and their data. So what Kylin do for them is to help them to process the data and provide it. For example, if we want to do their marketing precision marketing analysis, really we need to do the user profile analysis, and we need to process the user categories, user tags, and Kylin can help them to do that automatically. So you don't need to write the ETL jobs. You don't need to for example, maintain a lot of SQL script to that categorize or the user tags jobs. You can just simply define the user models in Kylin, sorry. And then whenever you have any change, you can just go ahead to the UI and change the models. You don't need to change the code. With that, you can have the better efficiency. And also Kylin can provide it the ability to process the data in advance. And whenever you want their user tags or user category, you can just fetch from the queue and it will be faster instead of you fetch it from like a traditional database, right? Because queues is more likely helpful when you are dealing with a multi-dimensional analysis, because normally you not only fetch their user tags, you need to join them together. You need to do the cross analysis together with other dimensions. Storing them in the cube will help you to analyze the data more efficiency. Yeah, as you said, to build a whole data platform, it's not just the Apache Kylin. You have to do the other works together with other tools together to implement the whole platform.
Yeah, that's assuming that it's in your case, assuming you have to know exactly what queries to build the queue
Yes. Yes. So for Apache Kylin, it's better to understand the business scenarios so that you can know how to build a model, how to build a cube, because we cannot build a model can cover all the scenarios, right? So that will make the cube very huge, and it will cost a long time to load the data. So normally we need to do is we need to analyze the specific business scenarios. We need to understand the business, and then design the model, design the cube for the specific business scenario.
I see. My last question is, so comparing back to Apache Druid and Kylin, and you did in your presentation, you mostly focused on use cases. I didn't go to the very deep technical architecture side. So in Druid, the setting up the Druid system is actually quite complex, and it has like 5 or 6 different services and daemons to have to run. And so in your cases, and how complex that system is.
Actually, Apache Kylin has a simpler architecture than Druid. I know that Druid has a lot of component in the architecture, right? You have to deploy like the coordinator or something. In Apache Kylin, actually, we packaged the whole installer in a simple package. You just need to put it in your Hadoop edge node. It's just a simple Java program, and it can be started by a Tomcat. And all the workload will be sent to Hadoop cluster or a Spark cluster whatever you have. So what you need to do is you need to prepare your Hadoop cluster, and then you need to prepare a single node for Apache Kylin. But if you want to do HA, you need to do more. You need to prepare more nodes, and then you just install Apache Kylin in that node. It will connect to the Hadoop cluster and submit jobs to the Hadoop cluster. That's all you need to do. And talking about the component inside Kylin, inside a single package, there are query engine, there are storage engine, and there are RESTful API server. There are metadata database. Yeah, that's pretty much 4 important components in Apache Kylin.
Okay, so anybody has, and this time, so we would like to open up, we're going to get a few minutes left, and I'd like to open up to speak to all speakers, and anybody has any questions for both Eric and Kai regarding both topics. So, you know, please, you can post your questions on the Q&A side. I guess not. All right, so thank you for the 2 speakers, both Kai and Eric, on the wonderful talk.